Hi, this is a video presentation for the paper, A Convolutional Deep Markov Model for Unsupervised Speech Representation Learning. I'm Samir Khurana, and this is joint work with Antoine Lauren, Weining Su, Jan Horowski, Adrian Langcookie, Ricard Maxer, and my supervisor James Glass at MIT CSAIL. So why do we care about unsupervised representation learning? One use case is data efficient speech processing. Current speech technology requires access to large amount of label data, which is not available across different languages. So unsupervised representation learning can help in developing speech technology for low resource languages. Another use case is language acquisition, where representation learning can be seen as the front end to complicated language acquisition pipeline. When it comes to defining representation learning, there's no fixed definition, and it depends on the downstream task at hand. In general, representation learning is just an alternative representation for your input signal, which in this case is speech. For example, for speech recognition, you would want to learn representation where the phonetic classes are well separated, and that would be considered as a good representation. When it comes to representation learning, a concept that has been around for decades is the autoencoder. It consists of an encoder that maps the input signal X to a low-dimensional latent space Y, and a decoder which maps the latent representation back to the original data space. And the model is trained to minimize the reconstruction loss. Uh, this kind of idea has generally been used for compression. Um, a more recent concept is a variational autoencoder, which combines ideas from autoencoders and approximate variational Bayesian inference. It You can also look at it as it augments the autoencoders with a probabilistic interpretation. So if you go in one direction, from latent space to data space, then you have a Bayesian generative model. Here you assume your latents are distributed according to a prior distribution, and your data follows a distribution that is conditioned on the latent space, which is transformed through a neural network decoder. And if you go in the other direction, then the encoder gives you approximate posterior over your latent space. And your encoder is also a neural network. And that's the key innovation of variational autoencoder. It allows you to amortize the cost of inference over the whole data set. This also means that at test time, given a new data point, you simply forward pass the data point through the pre-trained encoder to get the posterior estimate of the underlying latent variable. Uh, and the model is trained in a fully differentiable manner uh, by minimizing the evidence lower bound. The evidence lower bound, the objective function, consists of two terms: the reconstruction loss and the KL divergence between the posterior and the prior over the latent space. So in this work, we propose a convolutional deep Markov model, which is just a variational autoencoder with temporal latent structure. Uh, our model consists of an encoder, which is a deep convolutional neural network, a combiner function that takes in the encoded representation and the estimates of the previous latent variables to provide estimates of the latent variables at a particular time step. Followed by an embedding function, which transforms the latent sequence and upsamples it to the same length as the original input signal, which is followed by a decoder that gives us the mean of the likelihood function. And the model is trained as any other VAE to minimize the evidence lower bound. And KL in our case is computed analytically. The elbow is also fully differentiable. The model is trained using Adam optimizer. And to avoid latent variable collapse, we use a KL annealing with a linear schedule. And we use a mini batch of size 64 and train the model on a single GPU. Diving a bit deeper into the building blocks of ConvDMM, the encoder network is a 13-layer one-dimensional CNN. The CNN acts along the temporal axis, and it downsamples the input sequence by a factor of 4. And the last layer of the encoder has a receptive field of approximately 50. The embedding network transforms and upsamples the latent sequence to the same length as the observed sequence. It's a 4-layer one-dimensional convolutional neural network. And we use the activations of the last layer of the embedding CNN as the features for the downstream task. And finally, the decoder is a it's a low capacity feed forward network. And we use a low capacity decoder to prevent latent variable collapse, which is very common if you're using a very strong autoregressive decoder in a VAE framework. We compare our method against following self-supervised learning methods that are trained using only audio data: Mockingjay, problem-agnostic speech encoder, and Wave2Vec. Uh, Also, we compare against a multimodal representation learning method, residual deep audiovisual embedding network, uh, which was recently submitted to iClear, published in iClear actually. And finally, we compare the unsupervised representation learning systems with a supervised learning system. The supervised model is trained on the same data set as the unsupervised model with the same architecture as ConvDMM, and it is trained as a phone recognizer with ground truth labels. So we are basically here trying to answer the question, how far are we from the performance of a fully supervised system if we had access to labels for our unlabeled data set? And this is actually the top line for our experiments. We test the representations on two downstream tasks, linear phone classification and recognition. For phone recognition, we train a linear projection layer using the CTC loss to map the input features to output phone sequence. For phone classification, we train a linear projection layer using cross entropy loss to map input features to frame-wise phone alignments. And we do not fine-tune the ConDMM feature extractor on the downstream tasks. ConvDMM is trained on MFCCs, and we train ConvDMM on three different subsets of liber speech. One is 50 hours, 960 hours, and 360 hours. The 50 hours ConvDMM 50, which we call it, is comparable to PACE, which is also trained on 50 hours of liber speech English dataset. And ConvDMM 960, which is trained on 960 hours, is comparable to Wave2Vec and Mockingjay. And we do not train any of the representation learning systems that we compare against on our own. We use the publicly available pre-trained checkpoints to extract features from these models. And the linear classifiers, which are used to evaluate the features extracted from unsupervised systems, are trained on different subsets of Wall Street Journal trained data set, ranging from 4 minutes to 40 hours. So to generate the numbers in the table, we perform the following steps. So consider, for example, the column labeled 1%, as we describe how the numbers are generated for different models, which are different rows here. So we randomly pick 1% of speech utterances in the Wall Street Journal train data set. This is performed 3 times with different random seeds, yielding 3 different 1% data splits of labeled utterances from the Wall Street Journal train data set. We then train linear classifiers on the features extracted using different representation learning systems on each of the 3 splits 5 times with different random seeds. And this gives us a total of 15 classification and recognition error rates. And the final number in the table is the mean of these numbers after removing the outliers. Later, we'll also show the box plot with these numbers. In terms of, okay, so moving on. So first we compare the effectiveness of the latent structure. So we compare with a Gauss VAE, which does not contain, which is similar to ConvDMM, but it does not contain any latent structure. And we can see that ConvDMM significantly outperforms the Gaussian VAE, which does not have the temporal structure in its latent space. Next, in terms of phone error rate, the PER, ConvDMM 50 outperforms PACE by 23 percentage points, and similarly Mockingjay by 15 percentage points, and the multimodal system by 6 percentage points. That's the RDVQ. Under the scenario when 1% of labeled training data is available to the linear phone recognizer. Compared to Wave2Vec, ConvDMM outperforms Wave2Vec in the low data regime when 1% of labeled data is available. And in the high data regime, which in the 50% data regime, ConvDMM lags Wave2Vec by around 4 points. But it's still comparable to Wave2Vec. And so, yeah. ConvDMM PACE, which is a ConvDMM model built on top of PACE features instead of MFCC features, outperforms PACE features by 25 percentage point under the 1% label data scenario. And a significant gap exists under all data scenarios. Similar results can be observed with ConvDMM Wave2Vec, where ConvDMM model is trained on top of Wave2Vec features instead of MFCC, and it outperforms Wave2Vec alone. Especially interesting is the results on a low shot phone recognition. And here we are only using 4 minutes of label data. And as you can see that ConvDMM significantly outperforms all other methods. Surprisingly, the multimodal system shows excellent performance under this scenario. And ConDMM wave-to-vec, which is ConDMM model trained on top of wave-to-vec features, performs 10 percentage point better than the ConDMM, which is trained on MFCC features, and 38 percentage points better than wave-to-vec features alone. Um, so lastly, we compare the performance of features extracted using unsupervised learning systems trained on liver speech versus features extracted using the fully supervised system neural network acoustic model trained on the task of phone recognition on 960 hours of labeled data. The supervised system has the same CNN encoder as the ConDMM, and you can see that there's a big gap between the supervised system and all other representation learning techniques, even in the very few data regimes. So there's still a lot of work needs to be done. Finally, we show the box plot here. Uh, and the box plot basically tells us how stable our results are, especially in the low data regime. If you compare against wave-to-vec and pace, our results, which is the orange line shown here, are much more stable throughout. Uh, and the green line, which is a ConDMM wave-to-vec, ConDMM model trained on top of wave-to-vec features, is also quite stable and performs the best. And so to summarize, ConDMM features trained on MFCC features outperforms all self-supervised methods and is comparable to wave-to-vec. The inductive bias due to the Markov latent structure allows the ConDMM to extract the linguistic information from speech while ignoring nuisance information. And we hypothesize that the large performance gap between wave-to-vec ConDMM versus all other methods is due to the modeling of temporal structure in the latent space. So that's a common thing between wave-to-vec and ConDMM. And for the ongoing and future work, we are currently focusing on multilingual representation learning or language independent representation learning, and also on low resource speech recognition, and also on language acquisition. Thanks for listening.